Now in this video we are going to create delete a node method from AVL tree. Now here the first thing that I'm going to do, I'm going to create a helper function. So the helper function will be responsible for finding the minimum node. So as we said before, when we are deleting a node in which we have two children, in this case we need to find out the minimum node from the right subtree. So that's why we need a method for this. So I'm going to create our method like this. So the name of method will be minimum node. So here I'm going to declare it like this: public static binary node. So it's going to return the type of binary node because in this case we are returning the minimum node from this AVL tree. So it's going to be minimum node. Then as a parameter it's going to take binary node. So here I'm going to put root. So then the first thing that we are going to do, we are going to check that if this root's left child is equal to null, in this case we are going to return that root. Otherwise we are going to call this method recursively for left child. Now you might be interested why we are calling for left child, because in this case we know that the elements that are less than root node are located on the left subtree. So if we are looking for a minimum node, we need to look in the left subtree. So if condition will be like this: if root.left is equal to null, in this case we are going to return root. Otherwise we are going to call this method recursively for left child. So minimum node, so we are going to call it root.left. Now with this we have finished our minimum node method, so we are going to use this method inside delete node method. So after doing so, I'm going to create our delete node method over here. So it's going to be like this. So this method also is a helper method, so in this case it's going to return binary node. So we are going to put it like this: delete node, and it's going to take two parameters: binary node, which is the type of node, and integer value. So in this case our AVL tree is integer, so that's why we are going to delete the integer value from the AVL tree. So the type of the value over here is integer. Now then, as we said before, when we are deleting a node from AVL tree, we have two cases. The first case is a rotation is not required, and the second case is rotation is required. So what I'm going to do over here in the first part, I'm going to first find out the node, then I'm going to delete it from the AVL tree. Then we are going to check that if rotation is required, we are going to do rotation, otherwise we are not going to do rotation. So the first if condition will be like this: if node that we want to delete is null, in this case we are going to return saying that the value not found in the tree. So I'm just going to put system out print, so I will return message that the value not found in AVL tree. Now after doing so, I'm going to return node over here, because in this case the node does not exist in our AVL tree. I'm just going to return node. Now then we are going to check that if the value that we want to delete is less than this node's value over here, it means that we are going to continue to the left subtree. Otherwise, if it is greater than the node's value over here, we are going to continue to the right subtree. So the next if condition will be like this: if value less than node.value, in this case it means that we are going to call it for the left child. So it's going to be like this: node.left is equal to delete node. So first parameter will be node.left, and the second parameter will be value. Then we are going to check that if the value is greater than the node value, in this case we are going to call it for the right child. So I'm going to do it like this: else if. So I'm just going to copy this code from here and pass it over here. So it's going to be if value is greater than the node value. So this means that we are going to call it for the right child. So it's going to be right child. Now then, after finding the node, then in the else condition we are going to implement our three conditions in case of deletion of a node from AVL tree. So here in the else condition, it means that we have found the node, so we want to delete this node from the AVL tree. Now here we have three cases: if the node has one child, if the node has two children, or if node is a leaf node. So I'm going to implement them one by one. So the first condition I'm going to implement is in case if a node has two children. So in this case I'm going to check it now like this: if node.left is not equal to null and node.right is not equal to null. So this means that we have two children for the node that we want to delete. So in this case we need to find the successor of this node, and then we are going to take this successor and update in the place of the node that we want to delete. Then we are going to delete successor. So it's going to be like this: I'm going to create temporary node over here with the type of binary node. So it's going to be temporary node is equal to node. Then we are going to find the minimum node for the right subtree. So it's going to be like this: binary node is equal to minimum node for right subtree is equal to, we will find it based on the minimum method that we created. Minimum method, which will be the minimum node. So it's going to be like this, temp.write. Now after finding it, we are going to update the minimum node for the write node's value to the value of the node that we want to delete. So it's going to be like this, node.value is equal to minimum node.value. Now after doing so, we are going to delete this minimum node's value from the tree over here. So we know that it's located in the write subtree, so it's going to be like this, node write is equal to delete node. So we are going to call it for the node.write because it's located in the write subtree, and it's going to be like this, minimum node for write.value. So we are going to delete this one from the AVL tree over here. Now after doing so, we are going to check that if the left child is not null, we are going to delete left child because in this case we have only one child. Then we are going to do the same operation for the right child. So if in this case it's going to be like this, if node.left is not equal to null, in this case we have only left child, so we are going to delete left child. So in this case it's going to be like this, node is equal to node.left. So we are going to do the same operation in the else if condition for node.write. So if node.write is not equal to null, in this case it means that node will be, we are going to delete the write, so it's going to be node.write. Now in the else condition, we are going to set node to null because this is a leaf node. If it is a leaf node, we are just going to set it to null over here. Now with this, we have completed deletion of a node in the AVL tree over here, but after deleting, we need to check out that if we need a rotation or not. So to check out, as you remember, for insertion method, we have created getBalanceNode method over here. So here you can easily see that as a helper function, we have created getBalanceNode. So we are going to use getBalanceNode. Based on this result that we are getting from this getBalanceNode method, we are going to identify the condition, and based on the condition, we are going to do right or left rotation. So here, after deleting, we are going to create a variable which will take the balance that comes from the getBalance method. So here we are going to call it for the node. Now after finding the balance, we are going to check that if the balance is greater than 1 and the left node's balance is greater or equal to 0, in this case this means that this is left condition. So in this case we are going to do right rotation. So if condition will be like this, if balance is greater than 1 and we are going to run getBalance for the left child, so .left is greater or equal to 0, in this case we are going to do right rotation. So we are going to return rotate right for the node. Then the next if condition will be like this, if the balance is greater than 1 and the left node's balance is less than 0, in this case this means that this is left right condition. So I'm just going to take it and copy it over here. If the balance is greater than 1 and the left node's balance is less than 0, it means that this is left right condition. So we know that in the left right condition we are doing left rotation for the left node and we are doing the right rotation for the node. So it's going to be like this, node.left is equal to rotate left for the node.left. If we are doing left rotation for the left child and we are doing right rotation for the node itself. Now with this we have completed left right rotation also. So the next condition is right condition. So in this case, if the balance is less than -1 and the right child's balance is less than 0, in this case this means that this is right condition. So in case of right condition, we are doing left rotation. So I'm just going to copy this code from here and pass it over here and change it like this. So it's going to be if the balance is less than -1 and the balance of right node is less or equal to 0, in this case it means that this is right condition. So here we are just going to do left rotation for the node itself. So rotate left. Then the next condition is right left condition. So in this case it's going to be like this, if the balance is less than -1 and the right node's balance is greater than 0, it means that this is right left condition. So it's going to be like this. So in case of right left condition, first we are doing right rotation for the right child, so it's going to be like this. So node.right is equal to rotate right, and it's going to be node.right. Now after doing so, we have completed all 4 conditions over here. So we are going to return node. So with this we have completed our insertion method. Now here basically what we are doing over here is, so this part of code over here is same as with the one that we had in our binary search tree. Now after deletion we are checking that if we have any disbalanced node over here. So if we have any disbalanced node, we are making it balanced. So this increased the performance of the AVL tree over here. Now here, after this method, as I said before, this is a helper method for deleting a node from AVL tree. So I'm just going to create the delete method over here. So it's going to be like this: public void delete. So it's going to take the integer value. Now here, all we have to do, we are going to set root is equal to delete node, and we are going to call it for root node and the value that comes from this parameter over here. Now with this, we have completed our method over here. Now let's look at how this is working in practice. So inside main class, we have created an AVL tree over here like this. Then we have inserted elements to this AVL tree. Then we are going to call delete method for this AVL tree. Now here, after insertion, our AVL tree looks like this. Now in this case, if I delete 5 from here, you can easily see that our AVL tree becomes disbalanced. So in this case, this is right condition. So if I do the left rotation over here, after deletion, 15 from here will be the parent node, and the 10 will be the left child, and 20 will be the right child. So if I level or the traversal this, it should print out first 15, then 10, then 20. So after deletion, I'm just going to call level or the traversal to see the result. So if I run our code, now after running our code, you see that we have an error over here. So here inside AVL tree, by mistakenly I put value over here. So instead of value, it should be null over here. So if the node is null, it's going to return node over here. So if I run our code one more time, you'll see that first our AVL tree was like this. So when we are level or the traversal, it's printing out first the root node, then the second level, then the third level. Now after deleting 5 over here, our AVL tree becomes disbalanced. So in this case, after doing rotation, 15 becomes the root node of this AVL tree, and left child is 10 and the right child is 20. So as you can see, after deletion, the rotation works and it makes our AVL tree balanced. So as you can see, we have successfully implemented delete node method in AVL tree. Now let's see what's the time and space complexity for this method over here. Now first, we are going to start from the minimum node method. So as you can see over here, when we are creating a minimum node method, we are calling it for the left child. So this means that this method over here will take O log n time complexity. Now after finding this, we are going to continue to find the complexity of the delete node method. So in this case, when we are deleting a node from the AVL tree, as we said before, this part of code is same as with the one which we had in our binary search tree. So that's why this part of code will take O log n time complexity, because here, based on the condition, they are calling the method for the left or for the right child recursively. So this part of code will take O log n time complexity. So that's why this whole part will take O log n time complexity. Now then we are going to continue to the next part in which we are doing rotation. So we know that the rotation method takes O1 time complexity. So this means that these if conditions over here, we have for if condition over here, separately will take O1 time complexity. Now at the end, if we combine all these complexities together, we will get O log n time complexity. Now the space complexity is also O log n, because in this case, we are calling our methods recursively for the left subtree or the right subtree. So that's why we have to add left or right subtree to the stack memory. That's why it takes O log n space complexity. Now with this, we have come to the end of this lecture. So in this lecture, we have created a method which deletes a node from AVL tree. So after deletion, if AVL tree becomes disbalanced, so in this case, we are doing rotations to make our AVL tree balanced. So hopefully everything is clear about deletion of node from the AVL tree. So see you in the next lecture.